I invite you to the second lecture. I have there some picture which I have used as the invitation to some conference some time ago, but it is from the Himalayas, where I have left the step behind me with APO, which will be erased by the wind by this time, but anyway. So, we have spoken already about some requirements for passing the subject. So minimum is 12 points from the homeworks, 3 of 4 homeworks. Today we look at the first homework, which is more in the form of the form filling, that you fill and train and exercise the stuff which we will do during our seminaries. You can get some points for activity and team project, and then there is a exam and so on. So we have gone through the numeral system on the last lecture. If you have some troubles with it, I can stop on some of the topic of the numbers, but if you have idea how it works, we have spoken about the second complement or modulo complement, that we can use even the modulo complement even for a decadic system, if you remember. Basically that counting from, if we have 3 digits, so basically 9, 9, 9, 7. If we have a modulo which is 1000, then it is minus. Do you remember? I have said that it is, because if we have a modulo system, then basically if we have axis somehow this way, then we count the values up and up this way, and we do not reach exactly the 1000 because at that moment it is reset to a 0. And if we decide that we do not represent the unsigned range from 0 to 90, 99, but only the range from 0 to 499, then we can decide that that part here of the values going from 0 to 999 will represent negative numbers up to minus 500. So what is the 997? What is the number?
Minus 3.
Minus 3, yes. And for the binary system, it is much easier, because for binary system, we have only 2 values for a given digit. So we have there only 0 and 1. So basically, if we want to compute that it is minus 3, one option is to subtract a 3 from 1000 from the module. Or other option, which I have described, is what I can do, which is easier, to subtract the value from 999 minus 3. Do you see it? This way I get, yes?
Where can I find the slides?
So those slides are on the web. They should be there.
Yeah, but they are kind of different.
A little different, maybe I will update them.
Oh.
But this is the second lecture. It should be there.
Yeah, but they are a little different than the ones.
Not so much. I have updated a little, but it should be almost the same. It is computer arithmetic, and it should be almost the same. Okay, I will update it after the lecture, because I have done some small changes, but I hope that it should be similar. So, if I subtract 3 from 999, I get 996, which is not a complement to the module, but to the module minus 9. But it is easy to count, because it is very easy to count the subtraction of all digits at the maximum value minus any number, because in that case you have no borrow from the upper bits. So it is easy, but when we want to have a modulo complement, then we need to add +1. So it would be again 997. So this is how we can, for example, switch between the positive and negative value with the same magnitude. Okay, there is a short overview of the ranges for the data types which you know from the C language. It is the typical, because there is no guarantee for those sizes in the standard. Standard only said that integer has to provide a bigger range than -32,000 to +32,000, but doesn't say that it is that short integer should be of this size and long and so on, and integer of this size and so on. This is only the sizes which are specific for a given implementation. But for 32-bit systems and even the 64-bit systems today, it is similar. Okay, for 32-bit we have long, which is equivalent in the size to the integer, and only a long is longer. On the 64-bit systems, the long is already 64 bits long. Okay, we have looked there. I have made there a mistake. I have marked it in my previous presentation that we should there add the 7 and -6. So if we add it, then it is 1 plus 0, it is 1. 1 plus 1 is a carry, and 0. 1 and 0 and plus carry is again a 0. We have a carry, 1. 1 and 1 is a 0, and so on, till it propagates that there is a 1 which goes out of the representation. So at the end, 7 plus -6, even when we use an unsigned other, provides a correct result for the second complement arithmetic. We have seen that there is possibility to use the biased or XSK representation. It has an advantage that we work only with positive numbers in the representation and that it is linear. So it has the advantage that if we have a representation AX, then we basically go only up, and the arithmetic value is seen here, but the 0 is not the 0. So if we add two such values, then in the fact we get 2 times a k into the representation. So to correct this, we need to subtract the k once. Because if we use the other, which is for unsigned arithmetic, for this biased arithmetic, then it works this way. And multiplication is quite complex. This is not for the exam, basically. But you can, it is easy to count it, but the correction are nonsense and it is not used. We can have sign and magnitude. This representation is not useful too much for the computation. But today we will look to the real numbers, and in those real numbers we separate the mantissa, exponent and sign. So even this representation has some reasons to exist. Then there is one representation which is called a one complement. It has big advantage that if we have some number 0, 1, 0, 1, for example, which is +5, and we want to make a -5 from it, then we know that we only negate individual bits. But it has a disadvantage that if we have all zeros, then the negated value is 1, 1, 1, 1. So basically it has two representation of the zeros, so it is not so useful representation for many applications. there is an example. You can look at it on this cyclic arithmetic representation, or you can look at it on this modulo idea that basically we cut some range from the combinations for positive and negative numbers. We have seen that the others are quite a big problem, that we can have a simple other, but it provides a carry out, because if both input, 1-bit inputs are at 1, the result is 0, but we need to put somewhere the outgoing bit, so it is a problem. We need a full adder because we usually want to serialize them and build the adder for more than a single bit. There are the logic expression. Basically, the addition is relatively simple in the bit, so it is exclusive core of incoming carry and both inputs. It is a little more complex with output carry, which can be generated in the first half, where we add A and B, or in the second half, where we add the propagated carry to the logic. And this way we can build a ripple carry. Adder of arbitrary size, but problem is that it is very slow. It has advantage that it has something like 5 gates per single stage, but it is very, very slow. So we try to speed up the thing, and one option is that we build basic adders which are not directly coupled through the carry in and carry out, but they only define if the carry from a given digit will be propagated from the previous one, or if it is generated in the given digit. So this information can be computed only from A and B inputs, and we do not need to know what is actual state of the carry on the input. So we can pre-compute this information, then pass this information to the carry look ahead logic, and it prepares the information how to propagate carry through all this chain. So basically we can, if we substitute the actual propagation of the carry, we get those expressions. And as you can see, there is no A and B, because information about the A and B at a given position is stored in this information propagation or generation. So basically we generate at the given, and the bit which it is for C2, we can generate at bit 1 at the first bit, or there is a propagation from the previous bit, and bit number 0 has to generate the carry. So we can rewrite this task this way, and this way we can build much smaller adder, which doesn't have so long dependency chain inside, which is big advantage, because if we want to build a full carry logic, then we get to something like 10 power 20 for 64-bit, and it is quite a huge value. So I'm not sure, to how big computer, maybe that computer would be big as a small city or something like that, if you need so many for so many logic. Oh no, not so many. It is not so many still. So it is, no, it is, okay. It is, okay. It is interesting to compare then the size of the logic with the number, for example, of the sun grains on the earth or something like that. You easily can get to the sizes which are bigger. We usually do not want to build a full adder with carry look ahead logic because even that will be too big. So we build it from the blocks where each of those blocks use carry look ahead logic, and then those blocks are connected through the carry out and carry in. So it represents a smaller number of circuits, but those parts then needs to run sequentially. There is one option what can be done is that we build a generation of that propagation and generation for each pair of the bits. So we have there basically the 4 half adders in each of those blocks, which generates the information. Okay, we have there for each bit we generate the propagate and generate, and then we can build a combination that basically we know that if on the bit 0 or if on the bit 1 is no generation, then the generation will be 0. If it is 0 here, or if there is a 0 on the propagation and a generation on bit 0 is a 0. So basically you can combine that generation and propagation logic for the bigger blocks. So you can use more clock cycles or more levels of the logic which propagates and informs that then, for example, there is a generation or propagation of the carry from this block of the 4 bits. And you know again this information for those upper 4 bits, and again you know that this bit those can generate or propagate the carry from the lower part. So basically you can pre-compute the carry, the first, then you can run a backtrack and inform the actual stages if there is coming a carry from the previous group. It is no problem to compute this one, it can be computed directly, but this one gets there when we rerun the logic backward. This is marked as yellow, so it is not for the exam. Increment decrement is much easier. Basically, you need for the increment, if you have some number of bits, then basically a given bit is flipped only if all previous bits are at the 1. So basically at the moment when all lower significant bits are at the 1, then if we want to increment, that at that moment we need to flip this bit and put all the others to the 0. And again, if all the others are at the 1 and we are at the 1, then it is flipped. So the logic for the other is much easier and simple. So in the theory, we can build a subtraction as a negation and then addition of the 1, because we have seen that for the second modulo arithmetic, basically if we flip each bit to its opposite value and then add the 1, we have a representation of the negative value with the same magnitude as input number. But we do not need to add this one here and add there the logic to add the 1, because for the case when we use other anyway, we have there that carry in 0. So basically if we know that we want to subtract, we negate the bits on the input B, and then we provide and set carry in 0 to a 1 For the addition, we do not need to do that. Okay, for overflow, we have said that there are two options how to find if there is or if there is not overflow. One option is that we check that if we add a 2, for example, okay, if it is unsigned arithmetic, for the unsigned arithmetic, we know that overflow happens when we need a carry after the addition to the first bit, which is not part of the representation. So in this case, we see that there is a carry out of our 5-bit representation, so it is overflow. There is overflow. Only in this case, when there is a carry to the most significant bit, but not out of it, it is not an overflow. For the signed representation, we know that sum of two positive numbers cannot be a negative number. So if we add two positive numbers here, and even in this case, okay, it is negative and positive. No, there are two positive. If we add those two positive, but then there is carry that it change sign, so it is incorrect. If we add two positive numbers, but the result has most significant bit set, then we know that it is the overflow. If we add two negative numbers, then there is carry out, but if the result is still a negative, then this means that it is correct, because two negative numbers has to provide a negative number. So you see that if there is a carry in the most significant bit and there is a carry outside the range of our adder, then in such case there is no overflow. So this is the second option how we can check for the arithmetic overflow of the signed arithmetic. One option is that we check that for two negative outputs we get positive and vice versa, and the other option is that we check the carry in. If we add a positive and negative number, yes?
I was just going to ask that bottom one, why is it wrong? The minus 15?
Minus 15.
So why can't that work?
But it is 12. Okay, it is. Because we overflow in this case. We have got over the 16. So this means that we have overflow from the representation.
The overflow is the...
Arithmetic overflow, because we have added two positive numbers. So both numbers has most significant bit 0.
Okay.
We add them as unsigned numbers, because we want to use the same hardware for the signed and unsigned arithmetic, even on some computers or on most computers. In the fact, you do not have a different instruction to add and subtract a signed and unsigned numbers. It is the same instruction. Okay, not for the floating point. There it is more complex, yes?
So for this example, 12 plus 5 doesn't work, but if we had 12 plus 4, that's the boundary that would work.
Yes, if it is, for example, if we get rid of this, if we put this to the 0, for example, then it is 0 and 0, 1, 0, 0, 0, okay, 1, 1, 0, but there would be, if it is 0 and that carry from the lower bit, 1, so we get there the 1, but there will be a 0. So we find that 5 and 4 is 9, 8, 9, yes. 1, 0, 0, 1. So it is. So it works.
But if it was a 4-bit representation like that, it wouldn't work?
It is 5-bit in this case.
Okay.
If it is 4-bit, for sure it didn't fit. But if it is 32-bit, then we have no problem. If it is 64 and so on. So you need to be careful. What is the size of your representation? For sure, you can do the compiler automatically does some extension of the values. So for example, if you add the short int and int, it propagates the size to the bigger one. So in this case, if it is unsigned, then it is extended by the zeros only. If it is signed extension, then in this case, if the most significant bit is 1, it is extended over the rest of that representation by the ones. And we keep that rules that basically it is a complement to the module. We have seen that there is the option to divide by 2. It is same like dividing by 10 in the decadic system. It is easy. We only shift the digits. It is possible to multiply by 2. Again, we only shift the digits. For sure, if we do not keep the digits which we have shifted out from the representation, we lose the precision. On the other hand, if we shift to the left and most significant digit goes out of the of our range, or it changes the sign, then we have a problem. So we need a single instruction to do the shift, logical and arithmetic shift left, because those two are the same except for the detection of the overflow. Overflow for the unsigned is if the most significant bit gets to the carry from our range. For the signed, we find that there is overflow when positive number change to the negative or vice versa. For the division by 2, for unsigned numbers it is easy. We basically shift in a 0 on the left. If we want to divide a signed number by 2, then it is more complex, because in this case we need to keep the signed bit at the previous value. If we want to move to the left or to the right by more than the single bit, then we can use this so-called barrel shifter architecture. It can be a reverter even a little better, but in this case it is better to see in the concept. So basically what we know, we say by the number of bits which represents how many shifts. So this means shift by 0 or by 1. This sets shift by 0 or by 2, and this sets shift by 0 or by 4. And it is, in this case, it is barrel shifter to the right, so it is division, but it can be built same way even for the other case. So basically, what we can say is, if we, for example, want to shift right by 5, which is 1, 0, 1, so we want to shift by 5, which is 1, 0, 1. This means we switch this switch that we go this direction, so we shift by 1, we do not shift by 2, and we shift by 4. So if I have not made mistake, the bit 0 has been guided to the bit 5. Okay, so in this case, maybe it is MSB and LSB is vice versa, not a big problem. So basically, but you see that we can order this this structure to do that shift which we want to do. There is even one faster option where we have more switches, and when we decode to the actual values, but I would stay with this one. Multiplication, again, it is, I repeated from the previous lecture, but a multiplication in the binary system is really easy, because we do not need to multiply a digit by any other value than the 0 and 1. So if it is 0, then we in the fact mask the multiplicand at the given level. And if it is 1, then we provide it here. So when we start the addition, the first thing is that we say that it is the 1. So we copy the A here. Then we shift the A to the left, and it is again the 1. So we shift it to the left and we need to add it. Then it is a 0 bit in the multiplier. So in this case, we do not add the A here. We shift it, but do not add it here. And the last step is that we shift it here. And so basically the actual multiplication is very easy. But what is complex is to providing a sum of those individual partial results. We can build a logic which does a sequential multiplication in this case. So if it is 32-bit by 32-bit, then we have 32-bit here, 32-bit here, and in the fact this has to be 33 because the sum of two 32-bit values can exceed the range. For 8-bit, it is easier for the 8-bit case. You have 8-bit, maximum is 255 plus 255, so you can get 510. So it is more than the 8-bit, so you need 9 bits. So you need to add there 1 bit. And then you can shift right this block, and you can reuse part of this shift register that at the start you put into the MQ the multiplier, this B. So basically you put the B there, then you put the 0 to AC, you have A here, and you run one loop and a shift and loop and shift 32 times, and you only decide if at given stage we add the A or if we only copy the input. If the corresponding bit here is 0, then we do not add the A. Okay, there is the algorithm. So basically it said if the MQ0 is 1, then in such case we add the A into our result. In another case we skip it, then we shift right those two parts and we continue this way. And because we have a multiplier as put at the start into that bottom part of our shift register, then we get 1 bit after another here and we do the correct multiplication. There is an example on 3-bit values. You see that there is one input in the multiplier, so it is 5 by 6. We see that there is a 1 in the first case, so in this case we need to add. We put there the A, then we shift it right. Now we see that there is 0 here, so it is the second digit of the 5, second bit of the value 5. So in this case we do not add anything, we skip the step and only shift to the right. And in this case we again need to add the A to the value. So basically we have this value and we add the A in this. So 0 and 1 is 1, 1 and 0 is 1, and 1 and 0 and 1 is 1. So basically there can be a carry, so we need to have there that reserve of 1 more bit to store the carry from the addition. There is that example that we can resolve even with the hardware for the unsigned multiplication, the signed multiplication, but in such case we need to correct for the negative value that in the fact we have one modulo multiplication of the second element. So if the A is negative, then in the result will be the additional B multiplied by the modulo value. So we need to get rid of it. So it is this minus B shifted by the size of the output. It is not, probably this is, you only should have some idea that it is possible, but you do not need to, or you should be able to, ideally, to reconstruct this logic. If you try to write that basically a negative value, if we have A, then representation of the A is A, or for the negative one, if A was positive or 0, or it is a module minus the absolute value of the A, if the A is smaller than 0. But in the fact, because we know that A is negative in this case, then in the fact we can build the value as a Z plus A. Because we know that it was negative, so basically absolute value will be the opposite to the negative value, so it would be positive. So we can do it this way. And we see that that Z in the fact gets into our result. So this Z is to module 2 to n. Z is equal to n, so to the number of bits which are on the input. We can look at the multiplier as this series of the logical expression, because all our multiplication in the fact is multiplication of the two 1-bit digits, and it provides a 1 or 0, so it is easy. But we need to provide there that complex sum, and it is quite complex. In this case, it is easy. This least significant bit is already the result, but there we need to add together 2, there we need to add together 3, and so on. And because this addition of many components is complex, then, for example, we can try to build some tree which adds values together in the pairs, and then again in the pairs, and so on. So this is in the decadic, and we can even do another trick, that if we add the values, that we ignore the carries. So in the decimal system, we add there that 3, for example, 3 values, we add 1, 2, 3, and the result is 6. Okay, then we add a 9, 8, 7, and result of this should be a 24. But we put only a 4 to the result, and put a 2 into the carry part. Same here. 3, 7, 6 is 20. It should be 21, but we put only the result 1 there, and put a 2 to the carry out part. And same 3, 4, 5 should provide 12, but we put to the result only the 2 and the rest to the carry. And then again we can add those things together, so we add the 6 and 1 and 4, so it is in the fact 11. But we provide only the 1 to the result and 1 to the carry. And again, for the more significant bit, we add only the 4, 2, and 5. And it is again 11. But we put there only the 1 and 1 to the carry. And this way we can, and we have there the results are the carry, which we have not count into our sum, but we can do exactly the same with them, that we add only the corresponding bits or corresponding digits in the decimal system to the result. And if there is an overflow, we have another carry out. And again, we can again add the stuff this way. And only at the last step we need to add the carry outputs together with the actual value. So only once we need to build all that complicated carry propagation chain, which makes a problem. So we can build this so-called carry safe adder, which has the 3 inputs, provides the value sum of given bit, which are 2 XORs, and information if there is a carry in a given bit. But that didn't take care about the rest. So it is easier because it is not the full carry chain. And then we can build this system of those partial carry chains. Again, it is not for the exam. And we can build the system which adds those 2 together and provides the result. Computes those 2 together and provides the sum and the carry. And carry is then added to the, again, there we add those together in one go, those together in another go, and we can add the carry to one of those, and so on. So basically, in this case, we build so-called Wallace tree, which we have seen in previous lecture, which simplifies the logic, and you need to add there only the one full adder at the end of the logic. Okay, for the complexity of the operation, the simple bitwise complement negation is really easy. It is simplest operation which we can do. The actual hardware multiplication by 2 or division by 2 or by any value, by any bit, number of bits, is in the fact in the hardware really easy because you only rename the wires. If it is not fixed, if it is the variable that you can select by one register how many shift it should be, then it starts to be more complex, but we have seen that we can have that barrel shifter which works quite reasonably fast. Then the increment decrement, we have seen that in this case we only need to compute the logic end of the least significant bits and then flip a given bit according to at the time when all previous bits has been at 1, and there is an increment. Negate is even little more complex because we need to negate bits and that at the 1. Then is addition, subtraction, which are of the similar complexity. Then the hardware multiplier usually on the today's CPUs with that Wallace tree and carry safe adder and so on has usually complexity and the time, or complexity no, but the time to provide the result and latency similar to the addition subtraction. At the moment when you do not have it, for example at our simulator we do not have multiplication and division yet, then in such case the multiplication is much more complex than addition. And then we have a division, and there is no good way how to have very, very fast division. So there can be a logic which pre-computes through the table some reciprocal value, then you can try to somehow precise it, but if you want to compute a real division, then it is a problem. One option how to compute a division is we want to divide 7 by 3 in this case. We again can use the same logic which we used for the multiplication. So we have put a 7 here, and now we test if it is possible to subtract the 3. And we see if we can subtract it or not. So basically, because we put the divider to the upper bits and this into the lowers, then we see that at the start there is no result. At a given moment when we, okay, So we try to subtract, in this case, 3 multiplied by 4. So basically we move that 3 to the left by 2 shifts, or in the position, or in the fact it is not that we shift this left, but that we have moved this to the right. And one option is that we subtract the 3 multiplied by 4. And in the fact what we do, we check if the value fits into the 7 or not multiplied by 4. And we find that it didn't fit. So this means that we should put the 0 into the result. One option is then to return back to the value 7 and try to subtract 3 multiplied by 2. Yes, basically you can try, if you want to divide by some number, one option is that you multiply in the decadic system the divisor so much that it is aligned with the number. You know that if you want to divide, for example, 2, 7, 5, 4 by 22, then what we do? We first shift the 22 to the left, 22, and check. Can we subtract 22 from 27? Yes. In this case, it is 0 and 5. And 5, 4. We try to subtract again 22, or divide by 22. In the decadics, it is not only subtract, we need to divide. So we see that, so basically it was 1, to the result it was 1. Now in the 5 we have 55, we have 22. Twice, so we provide to the result the 2. And the result is that this is 1, 1, 4. And we try to divide 1, 1, 4 by 22. And it is 22, it would be something like 5, 5. I hope that I still can compute a division in the decadic system. Do you see it? It is in the decadic. You probably have tried this.
So this just follows the rules of long division.
Yes, it is exactly, it is one option. But we can do the other trick, because in this case we only know that it would be, result will be 1 or 0, because we do not divide by bigger, digit is not bigger than a 1. So in this case we can get only we divide, which means to subtract the divisor or not subtract the divisor. And there is one option that we subtract the value, compare it against a 0. So if it is negative, the result, then we know that there is 0 times the value inside. But we do not need to correct this minus 5 back to convert it again to the 7 and try to 7 minus 2 times the 3. It would be logical. But instead of the returning back to the 7 and trying if 2 times 3 fits in, which would, so the result is 1, we can do another option that we know that at this moment we have a negative value after this one because the result was smaller. So in this case, we, instead of the subtraction, we add 2 times 3. And if this addition overflows over the 0, then it means that we should write there a 1. If it doesn't overflow over the 0, then we know that we have got to the range. So basically, instead, it is 1. So basically, it is 7 minus 2 multiplied by 3. It is equivalent. So we can get to the result, and we do not need to do the 2 steps. First to test, and then second to subtract. but we can subtract the first and only look at the sign of the result. And instead of subtraction and addition, we need to, or instead of the subtraction, we need to switch between subtraction and addition to basically shift the range around the 0. So basically, it is something like binary search. That basically you divide the range to 1/2, 1/2, 1/2. So you use a 1/2 each time 1/2 of the divisor and shift the initial value by this attempt. There is a problem that at the end, if you want to have a real quotient, then that last subtraction has to be, if it is negative, the result, then you need to return back that you have a positive remainder and then correct quotient. So it is, but it is possibility, again, it is, I think that this is not for the exam, but that the hardware for division can be optimized this way, which is interesting. And it can be implemented again in this same hardware like the addition, but in this case we need the first to make, or maybe we need to first shift to the left to align the ones one after another. So maybe it can be a little more complex. So this is the algorithm. And you can try that it really works. And now we get to the real numbers. So you know probably a scientific notation of the standard decimal numbers. So it is similar. We first start with the fractions. So we can have a fixed point numbers. And if we add the bits after a decimal point or fraction point, then basically the first one is in the decadic 1/10. In the binary it would be 1/2 and 1/4 and so on. So it is because 2 power minus 4 and so on, 1, 2, 4 and so on are quarters and half is for quarters and so on. So basically we can extend our notation and counting of the arithmetic value such way that we can say that we can start with the minus j digit and go up to some I digit. So we have a longer representation and those parts are after the fraction point. In the fact, we can look at it a little different way. Basically, we can say that we have a representation where we multiply the values first by some unit. So basically, even in decadic system, if you do not want to work with fraction and you want to work with the cents, then if you multiply all values by 100, then basically you can forget about fraction digits. But problem is that we have there that k, which in this case is not a shift, but it is that representation of that smallest fractions which we want to work, basically. And the problem is that that if we try to multiply two such representations, so we want to have a result of x multiplied by y, but we do not want to have a special multiplier, but we will use a multiplier which includes which works with unsigned values. Then the multiplication is a problem because you get those cents in the fact multiplied by cents, and in the fact at the end you need to shift the value right by the correct number of digits, which has represent before the fractions. So it has some such problems. We can look even on the division and so on, but in that case we probably need the first multiply and then divide. So we need to multiply it by 100 and then divide by the second value, and we get the correct result if we used unsigned divider. Anyway, if we want to rewrite a decimal number, then you know that the scientific notation defines that the most significant digit, or that digit, first non-zero digit of the number, has to be in the range 0 to, okay, z minus 1, which is base minus 1. And if we have a base 10, it is 9. But if we have base 2, then we have only and it has to be a 1, from 1 to base minus 1. So basically, for the scientific notation, you know that the first digit before the fraction point, decimal point, is from 1 to 9. For the binary, because we can have only two values here, we know that there has to be exactly a single 1 before the fraction point. And in this case, we do not count the number. There it is 1, 2, and so on. It should be 14 decimal digits. In this case, it is 14 but binary digits. It is not the same number, for sure. If we want to convert this number to the actual decadic, then we can say it is 1 plus 1/2 plus 0 quarters, so 0, plus 1/8 plus 1 divide 16 multiplied by 2 power 14. And you get a decadic value. So it should work this way. If we want to have there a negative, then we can add there a minus. And for example, if we have a value which is very, very small, so this means that we need to move the most significant bit to the left as long as it appears before the fraction point. In this case, it is 1, 2, and so on. It should be a 16 bits below the that fraction digit. So in this case, we can write this number and multiply it by 2 power minus 16. For sure, we need to find how to store such data into the memory. And okay, this is the actual decadic value. Again, we count this, which is exactly the same value as this one, but with sign minus, and not multiplied by 2 power 14, but 2 power minus 16. So this way we can convert it between decadic and binary. And now we try to find a reasonable representation how to store those data into the memory. Why we want to work with this? For example, if you do some physical computation and you need to multiply the elementary charge of the electron with the, for example, mass of the sun or something like that, then basically if you want to have so wide fixed point representation, then you need thousands of digits for each number. But if you do not need the exact precise result, if it is enough, if you have a relative precision which is something like 1 to 16 millionths in the fact, then we can keep the representation in 32 bits. For all such numbers, we know that we have a relative resolution only 1 to 16 millionths. But for most computation, it is enough. For sure, at the moment when you start to count the distance between Earth and individual atoms on the Sun, then in such case, there is a problem that your relative representation would not allow to add those small fractions, so basically you ignore the distance. So at the moment, it is a problem. If you use, for example, MATLAB Simulink and you compute some simulation, it can happen that the Newton method starts to subtract two big numbers and the relative precision is very low, so it can be a problem. But anyway, we know that usually we can live with relative precision for such computations. That relative precision, if it is kept in the some range, that it is enough. So we define that we use the mantissa and the exponent, and that we represent that shift to the left and right by the exponent, and then we need to add the sign for sure. So basically the actual value is mantissa multiplied by base power to exponent, and we need to add there if it is plus or minus. And we usually use a mantissa in the range from 1 to almost the 2. So basically such mantissa which has a 1 before the fraction point, and the rest can be 0 and 1s arbitrary. So we cannot get to the 2, because if we add as many fractions as possible which are in that exponential range 1/2, 1/4, 1/8 and so on, then we never get to the 2. So for decimal it would look something like this. For the binary we have done there one change, that the power is now not written in the decimal, but even this 2 power 9 is now written in the binary. And such numbers can be easily represented in the memory, and there is a standard IEEE 754. It is based on some IBM and then Intel work and so on, and it is a standard which is used on almost all architectures. Basically, you can have a different size, width of the integers, of the characters and so on, but for the floating points, more of them keep this definition, because it is useful and algorithms are defined for it. And there are more possibilities how to store the data according to the required precision. So usually we have 32-bit, which is called a float in the C language, and 64-bit, which is called double. And in this case, the parameters are 1 bit for the sign, 0 positive, 1 negative, 8 bits for the exponent, and 23 bits for the mantissa. We will see that there is a one hidden implicit one later. For the 64-bit, we divide it to the 1 bit for sign, 11 bit for the exponent, 52 for the mantissa. For the neural network, who is there a fan of neural networks and artificial intelligence? Nobody? No? Okay, so I have something surprising for them, because for the neural network quite often it is enough count in the smaller relative precision, so they are quite often computed today only in 16 bits. So you have 16 bits which are divided to the exponent and mantissa. There is some another division which is done by Intel now, which moves some bits from the exponent to from the mantissa to exponent and so on. Sometimes we can use 128 bits representation and 256 bit representation. It is quite complex and it is usually not provided directly by the hardware. But you can build the arithmetic in the CPU which can compute with arbitrary precision. But you need many bits and you do not have directly the instruction for it. So you can take, for example, multi-precision, I think MPC computation, or what is the name of the library, which can compute for you with arbitrary precision. But if this computation should be fast, then you want to do it in the hardware. And we now look what is possible to do for the that 32-bit representation. It is what we try during our seminar later. So we reserve 1 bit for the sign. Then we have 8 bits for the exponent. Unfortunately, this last bit from the exponent overflow from the first byte, so it is there. And then we have 23 bits for the mantissa. And because we know that mantissa is in the range from 1 to 2 half open interval, then we know that we do not need to store this one into the value, because we know that this one is there implicitly present, except for one number, which we cannot represent this way, and it is the value 0. Because for the 0, we cannot allow any difference from the 0, so basically it cannot have this implicit one. We can look at the mantissa in the fact that this is a 23-bit unsigned number m, capital M, which we multiplied or divide by 2 power 23, that it is those fractions. Then we add the 1, we get those small m mantissa. Then we multiply it by 2 power exponent. But in this case, the exponent is not stored in the second complement, but it is stored in the excess k representation. So the 0 in the exponent is equivalent to stored value 127. Yes?
Could you maybe do an example of this?
Yes, we go through the examples. So this is the theory. We will focus on this 32-bit representation. The excess is 123 for double. It is all bigger, but the principle is the same. And for the exam, we have the examples for this. Unfortunately, it is you need to compute. Excuse me, but basically, how to test that you understand to it. It is by that way that you try to compute it, and it is a part of the first homework as well. And in the exam, we use the same rules, but only on 11 or 12-bit representation. So basically, it is easy to compute by hand. Because that 32-bit representation is sometimes quite hard.
So for that, the 11 or 12-bit representation, would it still be like the 1 bit for the sign, the 8 bits for the exponent?
Maybe. It is defined. You will find, because it is not the standard, you will find everything in the test. And if you do not understand the wording of the question in the test, then it is correct to ask during the exam. It is no problem. It is no problem to catch you that you do not understand the question. Problem is that you should understand the principle. But sometimes we test it by the way that you need to compute some numbers. Excuse me, it would be better to test your intelligence, not the ability to compute the numbers, but it is hard to test it. Okay, so basically, we have there mantissa, there is that 1 bit which is in the fact hidden, because it is that hidden one. Exponent, actual exponent is shifted by 127, and this way we can have this format stored. Okay, so it is easy. This way, again, it is exactly the same. We can have a problem that we can have a denormalized number. Denormalized number is like this, and it is not allowed. For the decadic system, basically, it has to start with the 1 digit before the decimal point. In this case, it has to start by 1. For sure, clean. But we can get to some troubles. Okay, there are examples how we can convert some values. So one option, for example, if you look at this, we have minus 12 and 625 thousandths. So in this case, we can count it such a way that we say minus 12 is minus, and 12 is 8 plus 4. And then this is 1/4 plus 1/8 in this case. Then in the next step, we need to shift the number to the right, that we get a decimal point here where it should be that we have exactly one before the single one before the fraction point. So we have moved it by 3 to the right. So to keep the arithmetic value exactly the same, we need to multiply it by 2 power 3. And okay, we know that it is negative, so the sign is 1. Then we know that we do not store directly the 3, but that we need to shift it by the 127, so it is 130. We can convert 130 to the binary, so it is 128 plus 2. If you look at this binary value, then I can convert it, that is 128 plus 2. I'm doing check that it is the correct value. So at the end we see that we store in the memory 1 because it is a negative. Then we put there this combination which represents 130, and it is in the fact information that it is plus 3. And then we put there this part of the actual mantissa, only that fraction part. We cut away that one because it is implicitly here. Okay, I will show you during the seminar more ways how it is possible to compute. Another example, in this case, 0.75 is in the fact 3/4. So it is 1/2, 1/4. But we need to divide it, or we want to move there the decimal point, that we look at it as 3 halves multiplied by 2 minus 1 in the fact. Because we want to be in this range from 1 to 2. Or you can write it directly, because you see that it is binary value, this binary value, and we need to move the mantissa. So it is 1.1. 1 is that hidden one, basically, which is fixed. So fraction is only the 1. And because exponent is negative, then we subtract the 1 from 127. So it is 126. So the stored value is positive 126, and then this one which represents that quarter which we need to add there, or it half quarter. And if we write it in the hexadecimal, then we take the group of each 8 values and 8 bits, and for each octet we can write single hexadecimal value. Yes?
For this, like the ones that you gave in the homework, they were all like ginormous numbers. They were like 1.7 something times 10 to the...
Yes, I give you the algorithm how to count with those big ones.
Oh, you're going
to... okay, basically the idea is simple. What you need to find the exponent, then you need to find what it is. The floor, I think that it is floor, power of 2 for a given value. You have some value, and you need to find exactly the same or a little smaller value which is power of 2. How you find this value? If we have some value x, how we find at which level, which is the first same or smaller power of 2 you have for this mathematical function. If you have such number, and I ask you for a decadic, find me a power of 10 which is first same or smaller power of 10. You say that it is No. Okay, 3 power, so 1000. Yes, power is, so it is in the fact a logarithm, decadic logarithm of this value.
Oh, so we're supposed
but a fixed part of it.
So we're supposed to find like the 2's power of the number that you give in the scientific group.
Okay, so basically what you do is, okay. It is way how you can compute it. Other way is to divide it by 2 and 2 and 2 as long as it gets to the given range. But it would take quite long time. But it is possible. But other option is that you and how you compute a logarithm of 2 of a given x if you do not have a logarithm of 2 on your calculator. You should know this from the mathematics, from math. You compute, for example, decadic or natural logarithm of given value and divide it by, you should know this, a multiplication of the logarithms, multiplication of the numbers is addition of their logarithm. The power is multiplication of the logarithms. If we do multiplication of the values and then logarithm, not multiplication, of the power. If we have x at y and we say that we want to have log of x and y, then we can say that it is log of x multiplied by y. And for the logarithm, if we want a different logarithm, then basically we need to find such power which makes a given base of the logarithm the value of the base which you want to use. So we use a logarithm of x divided by logarithm ln or log, it is, of the 2. You should know this from the, it was part of some math.
So that's natural log of both, ln?
Yes, or decadic, it is no problem. It doesn't matter because you divide the base of the logarithm. But it is for the seminar more this than for this computation. So there are more examples, but sometimes you can get into the big troubles, and again, those are real troubles which you see in the computers. For example, 1/10. Okay, so what is the 1/10? We try to multiply it by 2, it is still not bigger than the 1. We again try to multiply it by 2. At some moment we get that it is bigger than the 1, so we write the 1 to the result and so on. And at the end we get this value. But if you look at it, we have quite big problem because we never find it is periodic. It is same like in decadic system, you want to write 1/3. Basically, it is not possible to exactly write 1/3 in the decadic system. So you get into the troubles, and a decadic system doesn't match with the binary in the fractions. So be careful, and there are, yes, this is it is still not correct value of the 1/10. Easy to write it in the decadic system, there it is not possible. Okay, and there are another examples of such numbers which cannot be exactly represented. If you really need to count with absolute precision, then you need to work with a fraction arithmetic and use some complex libraries, and at some moment you anyway can get to the state when the resolution is not enough. Then we have some problems. What is, for example, division of 0 by 0? Can we say what is the resulting number? It is undefined. So we have a special value when all the bits of the exponent are 1, then this special value is reserved for the infinite and for the not a number. So if mantissa is non-zero and the exponent are all ones, then we basically cannot say what it is, and if you do any operation with this, then it's maybe signaling the error. It is possible to select if you want to get the exception, or if you want to silently propagate that the result keeps a none on those position in matrix and so on. So, what is a 0 divide, no, what is, for example, the 10 divided by 0? This is not fully defined. You know where on the axis we are. You know that you are somewhere very far on the right. So you can say that it is positive infinity. So there is a result that we can use a sign bit to say if it is positive or negative. Then we select all the exponent bits to the 1, highest value which is possible, and the rest to the 0, and it is the infinity. Okay, we have implemented the solution with the hidden reading 1, that first bit, because we know that the mantissa is in this range. But we can get again to the troubles. If you look there, so we are looking for smallest normalized number which we can represent. So what is that number? That number would be, in our representation, a 0 for the sign, then all the zeros, 8 zeros for the exponent. All zeros for the exponent would be 2 minus 127. And then there has to be a 1, because we have said that for the normalized number, it is not possible to have there a 0, because we do not have the place where to store that there is a 0. And what happens? If we add the 1, the smallest epsilon, and we want to go to the right, to the higher number, then we can add there a 1 and all 23 zeros plus 1 plus epsilon is the 1 on this. So basically it is 2 at minus 127 plus 2, and this is on the position 23 after the decimal digit, so it is minus 127 plus 23. So it would be 2, that epsilon for this arithmetic would be 2 to 127, 50, 60, 160. So we can go by so small step to the right, but if we want to get closer to the 0, then we have no way how to represent this gap. And then this gap would be 2 at power minus 127. Do you see? There is big difference. That basically from this place where we can represent the numbers by so small steps, so we can compute with relatively high resolution. Then if we want to go a single that small step to the left, near to the 0, here, okay, there, then basically there is a gap. We do not have how to encode the value. And it would make a problem, because sometimes you want to keep a relative, even if you lose the relative resolution, there is no possibility to keep it. Because in such case you need the index, you need the exponent which goes to the minus infinity. So you cannot have so long representation for the exponent. So at the moment when you stop the representation of the exponent at some location, then you have a problem that basically there is that impossibility to describe those steps even with that precision, that absolute precision with which we can move to the higher values. For sure, at the moment when we get to the value 2 at 126, then in this case our representation shifts, and next precision is only in the step which are of the twice time bigger size. So our precision, if you look at this precision, okay, I need to, so basically if we have there somewhere the precision, then we have there the relative gap that it goes. Okay, how it is? Absolute precision. Okay, I start somewhere here. So there we can go with some small values. Then we can go with the biggers and so on. So basically, our representation, if I write there a representation, and there's the arithmetic value, then in the fact, for the small values, there is some gap, and then we can represent numbers this way, then this, and so on. You see that as a value is bigger and bigger, then basically we use a small part of the representation axis. Those are the combination which we can encode into the 32 bits. Because you can look at it as to the function. So basically, we encode there when we are near to the 0, we encode by more values, the same range as there and so on. But there is a problem of this gap. So how it is solved? There is the representation decides that the exponent, which is all the zeros, is a special one. So it doesn't represent two exponent, this representation minus 127, but it represents only a 2 at power 126 in this concrete case, but without a hidden one expectation. So there is not implicit hidden one. And then you can have those denormalized numbers, and you keep the epsilon from the 0 up to this point on that 126 and minus 126 minus 23. So it is 2 at 100 minus 100. 159. So this is resolution with which you can move there. Then you can move with the same resolution here up to the 2 at minus 125, and then the epsilon is again 2 times bigger. So basically you keep the relative resolution till for all normalized numbers, and for denormalized you keep the absolute resolution. So there is absolute and then relative resolution. Okay. So there is the actual representation, what can be represented. So if all the bits in exponent are 0, then we can have positive and negative 0. If all the mantissa is 0, then if it is non-zero, if there is something, then it is that denormalized number. Then we have the positive and negative infinity, and there is smallest normalized number, so it has a 1 in the exponent, and all zeros in the mantissa, but there is that hidden one, so it is 1 and all zeros. So it is this actual value in the decadic system, so it is 10 power minus 38. And the biggest value which we can store there is that value with exponent one step before the infinity before the maximum. So it is 2 power 127 plus this value multiplied by this value. So it is something like 3 multiplied 10 power 38. So it is the range for the float. For the double, it is much wider because you have 11 bit for the exponent. And from this you can see why it is the offset is not 128, because if the offset of the exponent is 128, then smallest denormalized number would already overflow to the infinity. So there is the attempt that smallest normalized number, if you do a reciprocal to it, it still fits exactly to the representation. So this is the reason why it is this way. There you have some examples, some way how to compute the resolution. You see that epsilon which we have spoken about, no, 100, okay, 60, no, I have made a mistake, I cannot add 127 plus 26 plus, yes, 23 is not 50, but it is 40. Oh, okay, 46. Excuse me. So it should be 146. Okay. So this is the step, range, and so on for those numbers and some examples. So basically 1, for example, is 127 in the exponent, and in the mantissa all zeros, because that hidden 1 is there. So basically this 1 multiplied 120, okay, exponent with 127, which represents the 1. 1 half, it is not there, minus 1 is there, 1 half would be exactly if we decrement the exponent by 1. So it would be not 127 but 126, and the rest are all the zeros. Again, there is a comparison what are the exponent, what are the bias and so on, and the formats. And Intel even provides additional format which is 80-bit, which is non-standard, which has 16-bit or 15-bit exponent, 1-bit sign, and the mantissa, which in this case holds a hidden 1. So this is a special format which is used internally in the Intel floating point units for the computation, and it is more precise. So if you keep and compute some stuff inside the floating point coprocessor, you can get a different result on Intel and on another computers. And typically, if there is not that Pentium bug, which was quite funny, with the division, which was imprecise, then usually you get a more precise result. Problem is that if you use a 64-bit build of your program, then in such case a floating point coprocessor is not used, and we usually use a SSE unit with XMM registers, and it doesn't provide this support for extended precision. So on Intel it can be different according to the optimization level of your compiler and so on, what is actual precision of the result. For sure you can use a special libraries which has a higher resolution and so on, but they need to work in the software. Okay. Okay, so again this is still again the same, and we should now look how we add two numbers. If we want to add the two numbers, okay, I have there somewhere the summary. When we want to add two numbers, but they are multiplied by the different power of 2. For example, 1 is multiplied some mantissa A multiplied by 2 power 14, and we want to add plus, for example, okay, no, it should not be, it will be 1 0 0 1 something, and multiplied by 2 power minus 3, for example, then you cannot add the mantisas. It is not possible. You can add the mantissa together of two numbers only in such case that they have the same exponent, that basically you align the corresponding bits one after another. So if you have two numbers, then first thing which you need to know and find is which number has bigger exponent. So you subtract the exponents. You find what is the difference between the exponents, and then you need to move right, so divide by so many times by 2 the number with smaller exponent. This way you align the exponent one below another, the digits one below another, that they correspond, and you can proceed with actual subtraction. So it is necessary the first to find difference between the exponent, then shift the smaller one has to be shift right so many times what is difference between the exponent, and if both numbers has the same sign, then we can add the mantisas. If one of them has smaller, if one of them is negative, then we need to subtract. So in this case, we need to decide if the ALU should add or subtract the two values. And then at the end, what can happen? If we add two, in the fact 24-bit numbers, because we have the hidden one and 24-bit digits behind it, then what can happen? It can happen that we have the overflow, and that in the fact we have a 25-bit number as the result. And it is denormalized because it would have two bits before a fraction point. So for this reason we need to shift it by 1, right? And what it means to do with the exponent to have the same arithmetic value. What it happens? So we have a value which is bigger than 1. It is multiplied by exponent of the bigger of the input number. We need to normalize it. So we need that it is smaller than 2. So we divide it by 2, but arithmetic value should be kept the same. So for the exponent we need to subtract. No. If we divide the value, the mantissa, and the final number, which is combination of the mantissa and base multiplies power to the exponent, and the result should be the same. Add 1. Yes? Each time when we divide the mantissa by 2, we need to add 1 to exponent, and vice versa. So for the addition, it is possible that if we add two numbers in the range 1 half open to 2, 1 half open to 2, that result can be in the fact is in the range 1. Okay, no. One small one is in the range 0 to 2. Because that one is normalized, we move it. So it is one number, the bigger one is 1 to 2. The other is from 0 to 2. So the result can be from 1 to 4, but half open. So it cannot be the whole 4. It can be a little lower than the 4. And such number to get to the range 1 to 2, it means that sometimes we need to divide it by 2 and add 1 to the, balance it by the adding 1 to the exponent. If we subtract two numbers, and one is in this range and another one is in this range, what can happen? So if we know which is bigger, then it is possible that we can have the value from 0 to 2. So if we add a positive and negative value, it is possible that at the end we get even a 0. It is possible. And in this case, we need to multiply the mantissa so many times that we get it to the normalized state. And each time when we multiply mantissa by 2, to keep the arithmetic value the same, we need to adduce the exponent by -1. So this way we can get at the end the normalized number. What about the multiplication? For the multiplication, we multiply two values in the range 1 to 2 and 1 to 2, because in this case, in the case of multiplication, we basically can multiply mantissas, and for the exponent we do a simply addition. But in this case what can happen is that we can get a value in the range from 1 to 4. So it is again possible that during the multiplication we get the mantissa which doesn't fit into the normalized state, so we need to shift it right by 1. Okay? So there is the addition. Again, addition is more complex in the fact. For the multiplication, we can start directly multiplication. And if there is a problem, then in such case, we need to shift it by 1 to the left, and so on. In the case of addition, basically, we need to find which of two numbers has a small exponent. That one which has small exponent, in this case, we shift right by the difference of the exponents. Then we have corresponding digits one below another. And then we can add those mantissas together, and we can have a problem that the result, if it is addition at the end, that needs to normalization by 1 bit, right? If at the end it is subtraction because they have different sign, then in this case we can get to the trouble that we need to adduce it even more by the shift. Okay, so I think that we should stop. We have 18. We look at storing the values into the memory, and then we continue with the seminar that you practice this stuff. So if you try to look into the memory, then in Python it is quite hard to trick the interpreter that you interpret the values as they are stored in the memory. Basically, you do not have the access to the actual memory. If you have a C, then in C you can, for example, store those values directly as the bytes if the computer has a basic cell of octet bits and so on. So you can build the array with this value of in the memory, and then you can say that you want to look at this array as onto the single integer, and it reinterprets the value in the memory as an integer. So basically you can find that in this case this value on little Endian system will start with the 0, 0 and so on. So it is BF A0 0 0 0 0 hexadecimal value. So it is, as you can see, most significant bit is set. So if you interpret it as an integer, you get some very big, or not very big, some negative number. If you interpret it as an unsigned number, you get some number which is near to 4 milard, which is the maximum. If you try to interpret it as a floating point, you get again something different. Problem is that if you do this, there is no 100% guarantee what would be actual interpretation on a given processor, because it depends on the actual implementation of that processor. So it is possible that it would be this value, but it is possible that it stores multi-byte values a different way in the memory. So you probably know the Gulliver's Travel. I do not know if you know that fairy tale. And there was two camps, one which eats eggs from the big and another from the little end. And there is similar fight between the computer designers, what is the better way, how to store the values into the memory. So if you have pointer, for example, to this value, which is 256 byte in the memory, and you want to store longer, something which doesn't fit into it. So for example, we want to store 32-bit numbers, which is typical today, then we can start from the most significant bit. So this way, if we want to store this, then basically we take the 8 most significant bits, then the next 8 bits, and this bits, or we divide the number, basically we need to fill it that it has 32 bits this way. So we have 4 bytes which you want to store, and one option is that we start from the most significant, and another option is that we start from the least significant. And each of these mechanisms has some advantages. If we store the numbers from the most significant byte first, and though we do not have the arithmetic which can compute with a 32-bit advance, then it is easy to do the comparison, because if we have two numbers and point to two numbers by two pointers, then we first compare most significant bits. If they are different, we know that which number is bigger than the another. And we do not need to check the rest of the bytes. Then if they are same, we test another and so on. So for the comparison, and even for example for the network, if you send the address, it is better if the switch gets a most significant byte first, because it usually can route according to the prefix to the different networks. So for the network, it is better to send the data that you send a most significant byte first. On the other hand, if you want to add the numbers which do not fit into the registers of the processor, then it is better to add the least significant bytes first, then to have the carry, and then add the another. So if you want to have an addition which is longer than 32-bit, then in such case it is better to store data in the little endian manner. And there has been a fundamental camps, and it is interesting that on the network the big endian system is a standard, almost, or for TCP/IP it is standard. But in the computers today, for some reasons, maybe it is Intel that won or so on, even the architectures which used a big endian in the past has switched to the little endian today. So today a little endian is more common. Then important is that sometimes we want to have the values which are aligned. Because you want to have the values, it is faster from the memory if that memory is organized and not by single bytes, but today it is usually organized by 64-bit or maybe even by, in the cache and so on, by 256 bits and so on. Then we can address individual bytes usually, but if the 32-bit value or 64-bit value is naturally aligned in the memory, then we read it faster. So it is possibility to align, and by default compilers align the values. There can be a problem that if you, for example, use the structures in the C and you put some values, some fields one after another with different length, that you can build gaps in the structures. So it is good to optimize, and usually it is better to start with the those types which are longer and then add shorter and shorter one after another. So it is usually the best. Sometimes it is good to align it to the cache and so on, but it is for the later. And if we work in the C, then basically we should understand that we do not directly work with values in the memory, but we have some pointer. And that pointer points to that location. And even if we store somewhere the pointer, then again it is some value in the memory where we have a pointer which points to the actual value in some another place in the memory. So we have that possibility to reference and dereference operator. So in this case we get the address with ampersand of the given variable in the memory, and the vice versa with asterisk we can get the value which is at that address in the memory. So this is equivalent. This is equivalent as well if it is a pointer. And there are examples. The C provides a pointer arithmetic. So if we have there the address 0, 0, 0, there is the address FF. Then if we add 1 to the pointer, then we move to the next element of the same type. So if we have pointer to the integer, then we usually move by 4 to the higher values. C is usually the addressable unit, so we move by 1 cell. And if it is some double or some bigger, then we move, for example, by 8. And there is what is possible. So if we have the two variables and pointer to one of them, we can fill it by the address of the variable. We can set the value at that address. We can read the value. We can increment the pointer or the value at that address. So it is different if we write this or if I write plus plus, because I can decide if I want to increment the pointer or if I want to increment the value in the memory. And there is some rules that we basically cannot, if we provide information that the pointer points to the constant value, we cannot try to rewrite it. It is not allowed. If we say that it is a constant pointer, then we cannot move to the next element. And if we said that it is pointer to the constant variable and it is constant pointer, then we can only read the value and cannot modify it at all. So there are some basic pointer arithmetic. So basically you can see that we have some integer, some pointer to integer. We can assign the pointer by the address of that integer. We can increment integer, or we can increment. All this in this box is the same. We can say that we want to increment value at the given address to which the integer points, you see. Or we can look at it as onto the array. If we have array, then array in the fact is pointer to the first element. If we want to increment each element of the array, we can go this way, or we can set the pointer to the first and then increment the values at that pointer and move by the pointer to the next elements. And in the fact, actual increment of the pointer in the C is in the fact the cast of that pointer to the byte pointer and then moving it by the size of the variable. So, okay, so I think that we stop here. I have there something more about the memory, but we left it for the third lecture where I hope it fits.